And my today talk will be about embedding constants in Sobolev spaces, and it's based on joint work with my scientific advisors. Okay, we consider the Sobolev space WPN with Dirichlet boundary conditions. Just in case, I remind that the space of the functions such that the jth derivatives of f is absolutely continuous, where j from 0 to n minus 1 and nth derivative of f from LP. Okay, and let j and k be the embedding operator from WPN to WQK, where k is greater or equal than 0 and less than n. Then our embedding constant, lambda nkpq, it's the norm of this operator. So this is a wide enough problem with 4 different parameters. So the first results on it was obtained in 20th century for the case n is equal to 1, k is equal to 0. In 1901, Steklova found it for p equal to q equal to 2. In 1938, Levin found embedding constants for arbitrary p equals to q. And finally, Schmidt solved this problem for arbitrary p and q in 1940. As you can see, this formula which he obtained. Yeah. Here's p prime, it's p divided by p minus 1.
The embedding constant, huh?
Yeah, here.
But it was okay. It was not the best one. It was just a constant, but not the best.
The best one. Yeah, but only for case n and k is fixed. There are a lot of works between the first results and now, so I don't have a lot of time, and I mentioned only works about our special case. We consider the case of p is equal to 2 and q is equal to infinity and arbitrary n and k. In this case, we can consider the equivalent problem and study the functions a and k, which are the best estimates in the inequalities of such type. Then lambda embedding constant lambda nk to infinity, it's a supremum of these functions on a segment 0, 1. For convenient, further we omit the last 2 indexes and will write only n and k. How we can see later, this problem is closely related to Legendre polynomials and their antiderivatives. Here you can see Rodriguez formula for shifted Legendre polynomials. Usually it write with a tilde sign on the top, but for convenient we don't write it, and everywhere later if I tell Legendre polynomials, it means shifted Legendre polynomials.
M is a derivative. It's from to the x squared minus x to the power.
Oh, okay,
m.
okay, sorry, it's in m, yeah. It's a mistake. Okay, and let's define antiderivatives of Pm of x, the order of g, by this formula. Here's j is from 0 to m. Okay, in 2010, Karabin obtained a formula which connects a and k squared and n minus k squared, 0 squared, through some antiderivatives of Legendre polynomials. Also, he found a and k and lambda and k with k is 0, 1, and 2. How you can see on this formula, some indexes and the order of antiderivatives of Legendre polynomials do not depend on n minus k. So if we rewrite this with n minus 1 k minus 1 and subtract, we can obtain a modification of his formula, which connects just to next one, a and k, and n minus 1 k minus 1. And another one variant, it's also useful formula because it connects a function a with the indexes with same parity. This formula is very important because using the Kalabin's results, we can, for induction, calculate a and k one-to-one. So in 2018, we obtain a and k for k from 3 to 5. But when k is increasing, the problem of finding maximum of a and k on the segment became much more complicated. So we tried to find another approach using the properties of antiderivatives of Legendre polynomials. This is some results of Холщемников-Шейндулин, 2014. They obtain some formulas which connects different integrals of Legendre polynomial.
Why these polynomials are important?
Oh, okay. Here's a recurrence formula, and we know a and 0. Okay, we can.
They are here. Okay.
Yeah.
It's an exact formula.
Yeah.
And why do we have this formula? That is the question.
Why we have this formula?
Yes. Why one has this formula? This is got relation.
The Kalabin has this formula,
Okay.
and we modify it to this recurrence.
Okay. And why do you have an exact relation between this a and k, a n minus 1 plus k minus 1? Why there is such a beautiful relation here?
Простите, можно по-русски?
Откуда такое соотношение берется? Почему это соотношение взялось с полиномом?
Okay. You want to know how he obtained this?
Just a few words about it.
Okay.
Just a couple of.
It's made by f n from L2 by the definition. Yeah. Okay. And we can write it like a series of on the Legendre polynomials. Yeah. Yeah. And then it's f n. Yeah. And then f k of a squared less or equal than a and k on f n in L2. So these the best estimations which by Hölder inequality we can obtain. Also, they find the differential equation for integral of Legendre polynomials. Okay, now I can tell you about our main results. The first theorem is describe the derivative of a and k squared. How you can see, it's equal to product of two different antiderivatives of Legendre polynomials. Also, we proved that their zeros on interval 0, 1 are alternate, and the zeros of first polynomial correspond to the points of local minimum of a and k, and the zeros of second polynomial corresponds to the zeros to the points of maximum of a and k. In particular, if k is even, then 1/2 is the zeros of the second polynomials, and this is a local maximum point. And if k is odd, then 1/2 is a local minimum. It's 0 of first polynomial. Okay, the second theorem shows us behavior of A and K at the point of local maximum. It states that the values of A and K squared at the points of local maximum lying on the segment 0, 1/2 form a non-decreasing sequence, and at the points of local maximum lying on the segment 1/2, 1, a non-growing sequence. How you can see in picture, yeah, like we started at 0, and then first maximum, the next one is much more. 1/2, now it's even K, so it's a local maximum and it's the biggest, and then it's decreasing. And in odd K, the same way, but 1/2 it's a local maximum. So we obtain a very important corollary about A and K. For even K, the global maximum of A and K squared on interval 0, 1 is 1/2. And for odd K, the global maximum point is a local maximum nearest to 1/2. Okay, now we know that when K is even, the point of global maximum it's always 1/2. So we can calculate lambda and K just induction by the formula that I mentioned before. So this is theorem 3, where K is even, the lambda and K squared is equal to this ratio. And this is our embedding constants. So now we know something about the global maximum of A and K, and we know the embedding constants in case of even K. Okay, we have 2 more questions. What is the maybe general form of A and K? And what we can say about the case of odd K. To try to answer on it, I need to remind one more definition. Hypergeometric function defined as such series, whereas A and B it's complex numbers, but the denominator parameters are not negative integer or 0. AM is a Pochhammer symbol, and let's notice that if one of numerator parameter A is equal to negative integer or 0, then there exists M such that AM such that the AM minus 1 is not equal to 0, but AM is equal to 0, etc. The next one area is equal to 0. So if we have that, then this function is polynomial of order of M. So now we can see the theorem 4. Let denote x squared minus x by t. Then the functions A and K squared of t satisfy this equation, where I just told K is an integer greater or equal to 0, then minus K satisfies their conditions, and this is the polynomial of order K by t. So it's a polynomial of order 2K of x. This is the answer on the first question. How I told before, we a lot of work with the antiderivatives of Legendre polynomials, and in the process, in our work, we obtained interesting connection between antiderivatives and derivatives of Legendre polynomials. Here you can see if j from 0 to m, then we have such connections. On the left side, it's the antiderivative of the order j. And on the right side, we have polynomials, very simple view, and the derivative on the same order. Also, we can write it for the classical Legendre polynomials. Here, it's Legendre polynomials on the segment -1, 1. And using all of we said before, unfortunately, the case of what k is much more complicated, so we can obtain only conversion two-sided estimates, which you can see here. Just thought this conference is about spectral problems, so I say about application to spectral problems. The a and k to the power of -2 coincides with eigenvalue of such spectral problem, yeah, with Dirichlet boundary conditions. And so,
what is the problem? You have, what is the equation?
Oh, here. No, we should act on the both sides by y. Yeah, okay, maybe I should write it. Here on the right side, you have a delta function, okay? So we need to see on act. I don't know how to say it. Подействовать, в общем. By x. Here we have here's a from. Где? Да, я просто. Oh, sorry, I'm not finished yet. So if we rewrite it, we can obtain such equation. Okay. Like this. So it's equal to. Ah, okay, thank you.
Spectral problem.
Yeah. Okay, so now our embedding constants to the power of -2, it's a minimal, here eigenvalue depends on a. And the lambda nk means it's a minimal possible eigenvalue in this problem.